Hey guys, welcome back. Today is the 10th day of this 30 days lead code challenge. There seems to be a bug here. It still says day 9. Yeah, so it is this is the 10th problem that we are going to solve, and today's problem is mean stack. So let's get started. We are told to design a stack that supports push, pop, top, and retrieving the minimum element in constant time. So apart from the usual operations of push, pop, and top, we have to also implement this function which will give us the minimum element in constant time. So because of the constant time, it simply means that we cannot iterate through the stack and find the minimum element that is present. So these are the definitions of the API. So if we look at this class, we have to implement multiple functions, and the definitions of each of the function are given here. So push is a normal push element, pu push element X onto stack. So this is the normal push that happens for stack. Pop is as well same. So it removes the element on top of the stack. But if you look at the signature for pop does not return any element. So it just removes the element from the top of the stack. Whereas top will actually return the integer value. So um, so it it just returns the top element but does not manipulate the stack. And get mean does something similar, but it returns the minimum value that is present in the current stack, and it does not manipulate the stack. So they have given an example here to explain it better, but I have designed my own example. So let's assume that this is the stack, and since we are implementing each of the API, so we'll go from bottom to top. So we'll go in this direction. So let's say when we find that 0 is getting pushed, so the minimum element that is present in the stack up to this point will be 0. Now when we find 1, we realize that 1 will be pushed to stack directly, but the minimum element will not be updated because the new element is not less than the min that is found so far. So if you look at the stack from of these two elements, you'll find the minimum element will still be 0. The same thing happens when you push 2. So the minimum element does not change. But as soon as you push -1, the minimum element has to change because the new element is actually less than the current min that is found. So the min element will be updated in this case and it will become -1. Now it will continue to stay -1 as long as we do not find any element that is less than -1. So it will be same -1 for 4 when you push 4, and it will continue to be same when you again push -1. But when you push -2, the minimum element changes to -2. Okay, so now when the pop operation starts, uh, so as long as -2 is present in this stack, it will the minimum element will continue to be -2. And when uh, when the minimum element gets popped, it is not necessary that the minimum element the min in the top stack in the stack will change, because there can be same value element present somewhere below as well. So yeah, this needs to be considered. So we'll write our code accordingly. So what we'll be doing is we'll have to create a node which will store the information about which will store details about its current value, the minimum value, and there will be this, since this is a stack, so we'll have a reference to whatever node is pointing at the top. So let's call this as head, and the head will point to the elements that are present below the stack. So yeah, so our node will contain a value, it will contain a minimum value, and it will contain a reference to the next node that is present below the stack. Now apart from this, we'll need a node head for storing the top of the stack. Now in the constructor we won't be doing anything. Our push operation is the only crucial operation here. So what we'll be doing is we'll keep a reference to the old head, and which will be the current value of the head. And what we'll do is we'll create a new node for head, and say the value for the new node will be x. And for the minimum value, we'll have to check whether the old node is null or not, and accordingly we can take decisions. So if the old head was null, then this is the first element that is been pushed. So what we'll do is whatever is the value that is present in x, that will become the min value. And since sorry since there is nothing else to be done, so we don't have to reference head to the old value, because either ways it's null. Now if the old head is not null, then we can check what is the minimum value that was present earlier. So if old min for that is present in the old head, we'll extract that old min value, and we'll check if we find that x is less than or equal to the old min value, then our head will be the minimum value that will be stored in head in that case. uh, so if we find an element that is been pushed, if that is less than the old head's min value, or it is not present, then we'll just, or it is equal. So in this case, when I was pushing -1, it was equal to the old mean value. So what I'll do is I'll update my head with whatever value is being passed. That was the x that was pushed. In else part, what we'll be doing is we'll be just copying the old min value directly to the head, because the element that is been added is more than the old min. So the min will continue to exist, and what we want is our head, uh, which will heads next will point to old head. So our new node is now pointing to the old node itself. So our head is pointing to top of the stack. Now for pop operation, what we'll be doing is we'll be just updating the head pointer to the next node, and when it comes to top, whatever is the value that is present in the head, that can be returned. And as far as get min goes, so we will be returning whatever is the min value present in the head. So this should be sufficient for our case. The only operation that is crucial is this push operation. So yeah, and since we are doing the entire operation in constant time, so each of this method has a time complexity of constant time itself, amortized time. So let's run it and check how good our solution is. Yeah, so it matches the expected answer. Let's submit it and check if all the submissions. Yeah, our solution has been accepted. So let's see how well we performed. Yeah, our solution is better than 95%. So this works, and we have passed all the 18 test cases. Yeah, so this solves our problem. Oh, yeah, thank you. And if you like this video, please give it a thumbs up, and do subscribe, and click on that bell icon if you want to be notified tomorrow when I upload this new problem solution. Thank you.